So at this moment, you can see you got your NX tree and your NX ribbon up at the top. But with our integrated version, we now have 3DCS NX. Now, for those of you familiar with our software, you'll see all of the common icons that you're used to seeing. We have our own model navigation tree. This model navigation tree has all the information about 3DCS analysis. So if I start expanding it, you can see the base. This is where we have all the tolerance information. Because we're integrated, when I save this model, I would actually just say File, Save. And I would save it like I'm saving it in NX, and it would save in your Team Center. Why do we do tolerance analysis? The purpose of tolerance analysis is to understand and validate that if we go into production with our build process and our component part tolerances and our indexing method, we can meet our final dimensional goals. Those goals can be both quality goals, which would just be the gap and the flushness that you see out here on the outer mouse button, or functional goals, meaning validating that you can always assemble your product. You don't want to go into production and then have a certain number of builds where parts don't fit. All of that gets validated within 3DCS when you're doing your tolerance analysis. There's four main inputs to tolerance analysis: measurements, tolerances, and moves. We normally refer to them as moves, tolerances, and measures, but I started out with measurements because that's the first thing I want to talk about, which is what we want to analyze. If I click over here and I click on this, we're measuring the gap between the mouse button and the center frame. So these are the measurements that are written in the model, and I can click through here and you can see, okay, I'm measuring the gap here. If I go into these measurements, okay, so we were measuring this gap, and you can see the nominal gap is 0.8. That's what the design gap is. This is stating what is acceptable variation. So we're saying that gap can vary from 0.8 plus or minus 0.3. So first thing we do is we establish the measurements, which is establishing our goal. So we establish the measurements, which is what we're trying to validate, and then we have to write some moves. So the moves are already written. If I separate this, I can step this through the build process, and you can see it assemble exactly the way we intend to assemble it in production. So the moves are how we define how these components go together. The measures are what we want to analyze. And then at the part level, if I go into the base, the part level is where we actually have the tolerances. So now you can see that happens to be one of the features that locates the side mouse button. It's got a location tolerance on it. And so now when this number is changing because the model is not built, you're seeing component part variation. Every time this number changes, it's like we grabbed another component out of the box, it was molded, and this hole is within its defined positional tolerance. That happens to be the locator for the button. So then when I build this and actually utilize all the moves, now when I deviate it, you're actually seeing the effects of the component part tolerance on the location of the button. So if I go to the base, now you can see I'm going up to the NX tree. This down here in the base here, this is the DCS navigation tree. This base is the NX tree. If I go into the base and I say make display part, you can see that this base has got embedded PMI. It's got the defined tolerances defined with the actual CAD data. Because this information exists, the process becomes much easier in 3DCS for NX. So you can see that there's no tolerances. Well, this is DCS tolerances, but they're all turned off. There's no GD&T in the base. But we saw that there was GD&T actually in the base in the CAD system. So now I can come up here and I can just say update PMI. And I can update the GD&T for the whole model, or I can just pick the base. And when I pick it, you can see that, oh, I all of a sudden have GD&T again. Now my model is complete, and I can actually do a nominal build and run an analysis. I'm going to build 2,000 mouse assemblies, and we get our statistical results. So this is the left cover to top cover gap measurement, and you can see that my range of variation is 0.6 millimeters. And because we said it could vary plus or minus 0.3, we're pretty much there. We're within spec, we're failing 0.4% of the time. However, if I go to the next measurement, which is up here at this tip, you can see that I'm failing a lot more. You can just see that the tips of these are moving around a lot more than what's happening back here. And that happens to be not just a function of tolerances, but it's a function of the move. Because of how we're locating this piece to the top cover, it's getting amplified by 2.64. So that 0.3 millimeter tolerance is acting like a 0.9 millimeter tolerance. So this helps you understand that, hey, it's maybe not just a tolerance problem, it's a location problem, and you should modify your locating method. If you can't, go to this tolerance right here, which position left right cover, position left right cover, double click it. I'm going to change that tolerance from 0.3 to 0.15. Go to the same measurement. So now that tolerance, you can see, man, it's still the #1 problem because it's getting amplified. But you can see it's 0.15 now, and my variation went from 1.55 down to 1.27, failing 26% to failing 25.5%. When you're done and you need to create a report, you click this button here. And this is what pops up. So with a button click, that's just the home page. Then you have a model summary. But the key, I guess, would be the simulation results. So here's all of my measurements, as well as you can go to your model inputs,